speaker is Shyh-Dar Li from University of British Columbia. He got his PhD from Li Funk lab, and then he moved to Toronto, then moved to UBC, Canada, and he's now the associate professor there. He's one of my friends, and then for the last couple of years, I severally visited him to collaborate research. Are you ready? Okay, please.
Okay, thank you so much for this opportunity to share my work with you. So I just want to quickly jump to my talk because I prepared a lot of material. I hope I can cover everything in 20 minutes. You certainly don't need introduction about the standard methods for making liposomes, but very briefly we use so-called thin-film hydration and membrane extrusion to make liposomal SUV. Then we perform dialysis to create SUV containing a transmembrane gradient so that when we mix an amphipathic drug with this SUV, the drug can be actively loaded into liposomes. So this is the standard way of making liposomes, including the clinically approved Doxil. So my lab is actually interested in sort of expanding the standard active loading methods to water-insoluble drugs so that we can deliver more more variety of drugs. And recently, we're also interested in applying new technologies in making SUVs for drug targeting. So today I want to cover my talk. Cover these two topics in my talk. And so I don't really need to explain this slide, but basically we developed this so-called solvent-assisted active loading technology, abbreviated as SALT, to actively load water-insoluble drugs in the inner aqueous core of liposomes to really address one of the key limitations of the standard active loading. That is, the standard active loading method is only applied to amphipathic drugs. So this is how we envision this technology is working. So first, again, we still have this liposomal SUV containing a transmembrane gradient, but during the loading, we include a very limited amount of water miscible solvent. And then we add this insoluble drug in the mixture. So the water miscible solvent is there to prevent precipitation of the insoluble drug, mainly to keep the insoluble drug in the soluble form, but in the meantime also increase the membrane permeability to enhance penetration of this insoluble drug into the inner core to form complexes inside the liposomes. And at the end, we just perform dialysis to remove those solvents. So this is the concept. So the first model drug we tested was Starsporran. So structure is shown here, very hydrophobic, although it's a weak-base drug. So even you adjust the pH to very low, it's still not soluble. This compound is only soluble in DMSO. So we still prepare this ammonium sulfate gradient liposomes. And in next study, we actually compare the loading efficiency with when we perform the loading with either without DMSO or with 5% DMSO. So 5% DMSO is just enough to keep the drug soluble in the loading mixture, and you can see this dramatic difference. And I also want to point out that the drug-to-lipid ratio is pretty high. And just to verify that the drug is actually loaded in the aqueous core, we perform the cryo-TEM and show that those STS molecules are indeed precipitated inside the liposome. So the next step is that we want to test that this technology is also working for geologic acid, which is a weak acid drug. So this is again, very hydrophobic drug, and it contains an acid group, so it's a weak acid drug. And it's an API isolated from a Chinese medicine. It has many very unique mechanisms for anti-inflammation, anti-angiogenesis, and anti-proliferation. So people believe this can be a drug, but the problem is that the delivery is really a problem because of the solubility, and also the free drug is quite toxic to RBC, red blood cells. So again, we developed this active loading gradient copper acetate, but we adjust the pH to enhance the loading of this weak acid drug into the core. And during the loading, we also put water miscible solvents. And because this drug is soluble in multiple solvents, so we got to test a variety of different solvents from DMSO to dioxin. And we found actually all of them work, and the best are DMSO and acetone. So this formulation is shown by using this acetone assisted loading here. Very beautiful color here, and the size is about 80 nanometer, very good loading. And I just want to point out that, as I mentioned, this drug is very insoluble. The solubility in water is less than 5 microgram per ml, but with the salt technology and liposomal formulation, we were able to increase the apparent solubility to greater than 10 milligram per ml. And then this makes it easy to deliver in vivo. But just before I jump into the in vivo data, I want to talk about the working mechanism for salt. As I mentioned, because this drug is now soluble in a variety of solvents, so we were able to check whether different solvents will work. And the answer was yes. So we can use different water miscible solvents and to improve drug loading of this compound. The next question is there an optimal concentration of the miscible solvent to promote loading? And is it dependent on different solvents? So we performed this relationship study between the solvent concentration in the loading mixture and the final loading efficiency. So I just want to briefly summarize the data because it's a lot of work from the students, but for every solvent we have tested, there is always an optimal range of the solvent concentration that can achieve either complete drug loading or near complete drug loading. So the optimal range should be above the concentration of solvent that is needed to completely dissolve the drug. But it cannot go too high because once it the concentration goes too high, then the drug loading is actually decreased. So the data suggested that the solvent is actually doing multiple things. The first mechanism might be just keep the drug in a soluble form so that they can pass through the membrane. But second is that it might also increase the membrane permeability to allow the drug to pass through the bilayer more efficiently. But again, we cannot increase the solvent concentration too high because it will open up the liposomes too much and then causing a gradient collapse. So then we won't have good loading. Again, back to the efficacy data. So first thing we look at is the hemolysis. As I mentioned, the free drug is very toxic to RBC. So as you can see, free geologic acid is like, just likes the RBC like a detergent. But once we put them in liposomes, the toxicity is gone. And then we quickly look at the efficacy in two tumor models. These both are subcutaneous tumor model, one with breast, one with melanoma. And the results were very comparable. So you can see the orange line, which is free geologic acid. We cannot dose too high because the drug is quite toxic. And you can see that basically the control and the orange line are overlapping. And but the equal dose lipo-GA, we can see significantly enhanced efficacy. And if we further increase the dose to 20 mg per kg, then we can, in this model, we can completely suppress the tumor growth. And very comparable results with melanoma. Then I had this crazy idea about, okay, I don't just want to do cancer. Can we think about a different, that no one has ever touched topic? And then this project came to mind, that is a pediatric formulation. And we work with a compound, model compound called mefloquine. This is a melanoma drug, anti-malaria drug. So you can see the structure here also still very hydrophobic, and we can load this drug into the aqueous core of liposomes using salt technology. Okay, so I thought, well, maybe this could be an interesting pediatric formulation for kids, because now we are making this insoluble or polysoluble drug in a aqueous formulation, so it's easy to swallow for kids. And second, now we are loading these very bitter drug molecules into the core of liposomes, preventing direct contact with the taste buds. So we should be able to mask the taste of mefloquine. And we only use PC and cholesterol to prepare our formulation, so they are very safe for kids. And so they just performed the first study. But I just want to highlight the significance of the malaria, especially in developing countries. They are still the most deadly diseases in those countries. And children under the age of 5 are the most affected population, just because the drug is so bitter, those children just cannot swallow the formulation. So far, there's still no pediatric formulation for this drug. So I thought, well, maybe our technology can do something to help. And the first study we looked at is whether the liposomal formulation can actually mask the taste of the drug, mefloquine. So we are collaborating with Colin Ross at Washington State University, and they are using e-tongue to measure the bitterness of different formulations for us. So it's a very straightforward measurement of taste. So in this case, they are looking at bitterness only, because the drug is known for its bitterness. So we have sugar, 10% sucrose. So the score is negative because it's sweet. And we have mefloquine suspension, the standard formulation that is currently used or compounded in pharmacy in Africa for children to use. Is very bitter, 500. And so look at our mefloquine liposome, it's just as sweet as sugar water. And next, we really want to understand the drug release profile, because what we really want to achieve is the drug is not released in the oral cavity, but is quickly released in the stomach or intestine. So we first look at the simulated saliva and comparing mefloquine suspension and mefloquine liposomes. These two are very similar. The only difference is the different drug-to-lipid ratio. As you can see, our formulation is not released in saliva, suggesting it should not cause bitterness taste. And then we look at the release in gastric fluid. Very quick release in the gastric fluid for both suspension and liposome formulation. And so the mechanism could be that because the pH is pretty low and the phosphate group in the phospholipids are protonated and then decrease solubility and induce instability of the liposomes, promoting drug release. And we also look at the drug release in simulated intestinal fluid, supplemented with a bile salt. So again, very good release. So this is what we want. But how about oral bioavailability in mice? So we look at the pharmacokinetics at different time points. And you can see that, so we have mefloquine suspension and we have a liquid mefloquine. Basically, they are both bioavailable. They have very similar bioavailability. And I just want to mention that we were also able to produce lyophilized mefloquine liposome. So in the hope of preparing an oral dispersible formulation for this drug. And then my lab is quickly moving into the tumor immunotherapy. So this is sort of a new project in the lab, and we're still doing a lot of research around this topic. But today I want to just share some preliminary data we have got. So we are really interested in very difficult to treat tumor. So in this case, we are focusing on intraperitoneal metastasis. So again, they are very difficult to treat and normally incurable. And one thing that they found in common is that their tumor immune microenvironment, or so-called time, is highly suppressed. So this suppressed time is actually promoting tumor to growth and progress. And so, as you know, immunotherapy now is a very hot topic. So people have tried different immunotherapy for IP metastasis, and they have found very significant improvement, especially if the drug is delivered through the IP route to basically enhance the retention of the treatment in the tumor microenvironment. So our hypothesis is that maybe we can use the salt technology and liposomal formulation to enhance the retention of immunomodulating agents to further help immunotherapy for this difficult disease. So the drug we are interested in is RA4A, is a toll-like receptor 7/8 agonist. Again, very hydrophobic. So before we load this drug into liposomes, first we were curious about, what kind of formulation would have a better intraperitoneal retention. So basically, we did very similar work as Yvonne presented earlier this morning, and we got very similar results as well. So in this case, we're only interested in the charge effect on the IP retention. I just want to direct your attention to 4-hour because it shows the most significant difference. So again, the cationic liposomes are showing the best IP retention, and next is the neutral, and the worst is PG, negative formulation. So then we just load this drug into the DS-TAP formulation, and then look at the drug pharmacokinetics after intraperitoneal injection. So what we really want to achieve is having better retention in the peritoneal fluids and better delivery to the IP cells, and reduce the absorption or retarded absorption in the plasma. And we achieve everything with the DS-TAP RA4A, the red line here. So we were really encouraged, and then also the next topic we look at is the cytokines we were able to induce, and so we actually look at 3 cytokines now, but this is the most significant one, is interferon alpha, which is known as the key regulator for tumor immunogenicity. And as shown here, our DS-TAP formulation is the best in terms of promoting production of interferon alpha. And we quickly move into the efficacy study. So we first inoculate CD26 luciferase cells into the IP cavity, and then 4 days later we treat those mice with IP oxaliplatin, which is a known immunogenic cell death inducer. And the next day we inject either PBS, free drug, or DS-TAP formulation. So this model allows us to follow the tumor progression very easily because you can image them, and also you can quantify the progression as well. But I just want to direct your attention to the bar graph shown on the left-hand side. So you see this oxaliplatin only group, but it's not really slowing down tumor progression. With the free RA4A, you can see some improvements in early time points, but very quickly rebounds in terms of tumor progression. But with DS-TAP RA4A, you see this more long-term effect in this difficult model. So the data suggests us that the free RA4A is only having this transient effect, probably due to cytokine induction, but the effect is to withdraw very quickly. But with enhanced retention of RNF4A, we were able to induce more long-term efficacy. So I think our next step is really look into the mechanism like Dr. Akita just presented. So I want to quickly move into my second part of talk, which is using microfluidics for making SUVs. So Ivan already talked about this staggering herringbone microfluidics, so I'm not going to repeat that. But I just want to say that we are actually working with very difficult formulation. So this formulation only has cholesterol and twin AT. And our job, or my goal, is really push the cholesterol to the highest limit so that we can make the formulation really stable, but again, also reduce the twin AT concentration to reduce the toxicity. So with the microfluidic technology, we were able to push the cholesterol content to about 83 more %. And so that significantly increased the membrane permeability. So now we can load a drug actively. So in this case, we load doxorubicin as a model drug. You can see the spindle shape in the inner aqueous core. And very interestingly, we just recently published the data showing that the so-called phospholipid-free SUV formulation has really good selectivity towards liver. And when we do the section, by the way, I just want to mention it, 5 minutes after IV injection is all in the liver. And inside the liver is actually everywhere. It's not Kupffer cells, but also mainly hepatocytes. So we are very encouraged by the results, and we are now thinking about how to use this delivery system to deliver other drugs to overcome some medical challenges. I want to thank my lab and collaborators and the funding, but I want to use the last 1 minute just sort of advertise this Nanomedicine Innovation Network. Funny, we have the same name as Yvonne's organization, but Canadian scientists just received over $40 million federal funding as well as industry support to establish this initiative, and which is led by Peter Collis. So I just want students and postdocs to know that we will be heavily recruiting across Canada, so watch us. Thank you.
Dr. thank you very much for your nice talk. So, do you have any? Please.
Thank you for your talk. So I wonder why this salt technology is limited for amphiphilic compounds. How about, for example, like cell membrane soluble proteins?
Highly soluble protein.
For like cell membrane
protein.
Proteins.
No, our technology is not developed for protein. We are working with new technologies that hopefully can load different proteins into our particles, but we are not there yet.
And also, what is the physical state of the precipitated drug inside the liposome using the salt technology? Is it a crystalline or amorphous?
We don't know. We believe it's crystalline, but we don't have data to support that.
Thank you.
Yes,
Yeah. So here, very impressive. So you have that cholesterol, phospholipid-free liposome technology, and I have two questions. One is that why do you want to make a phospholipid-free technology? What is the advantage of this over the phospholipid conventional liposomes? One, and second, how does this technology fare in terms of the stability and the delivery? You have some data on that?
Right. So the project was actually started as a curiosity-driven research. So we were just curious of what the technology can do, the microfluidic technology can do. So then we work with cheap lipids like cholesterol and twin AT. And later on, it turns out it has really unique bio properties compared to the standard pegylated liposomal doxorubicin. So it's interesting. So we are still looking at possibilities for using this technology to enhance or to address different medical needs, right? So in terms of stability, it's very, very stable. But we're still in the process of monitoring the stability. But so far, like 3-4 months is still very good, right? And do I answer all your questions?
Yeah, you did. Thank you.
Yeah, okay. Due to time limitation, please give a quick question and a quick answer. Thank you.
Yeah, regarding these phospholipid-free vesicles, you use polysorbate 80. I think this is absolutely the wrong way to make formulations, because polysorbate after IV is very allergic, causing allergic reactions. So I really don't understand why you are investigating this, sorry to say, but please work with phospholipids, I would say. And I'm not using synthetic detergents which are causing anaphylactic shocks. This is not the way to make.
Okay, yeah, I think that's a good question. So we really need to look into the toxicity, but we haven't seen anything yet. And also cholesterol twin 80, they both approved for IV formulation. But I think your point is
side effects, and maybe you didn't see a lot of it is clinically very well validated as these synthetic detergents are causing side effects. So you should take that into consideration.
Okay, thank you.
A short question, please.
Thank you for a very interesting talk. And gamma-sic acid, does solvent type affect encapsulation efficiency and the residual concentration of solvents after purification?
Yeah, so yes, the optimal solvent concentration is dependent on the solvent, and my impression is that DMSO and acetone are the best among all, and the residual is less than 5 ppm, so very low.
Thank you.
Quick comment just about the fact that the salt technology, I like your approach a lot, because many people are trying to put hydrophobic drugs in liposomes, and those are extremely difficult to formulate because they are not compatible with the liposome bilayer, and they cause lots of problems. But my question regarding that technique is, do you need, what is the trap that you are using? Do you need different traps depending on the drug that you are using?
Yes.
And this is one part, and the other part is, how stable is this system in terms of shelf storage? And can you answer those?
Yeah, so sorry, the first question was?
The first question is,
the different
trap,
loading.
you design
Yes.
a special trap for each different hydrophobic drug you want to put in.
Yeah, you need to optimize that too.
And you have traps for everyone. Suppose, for instance, for curcumin, can you apply this
Curcumin
method?
Different, yes, but different transmembrane gradient.
So you need a special.
Yeah, you need to optimize the transgradient as well.
For chloroquine and mefloquine, you are using ammonium sulfate, I guess, right?
Yes.
And then how stable are those formulations?
So far, pretty stable. But again, in the academic lab, we don't monitor them forever. So just a few months. Right.
Thank you.
Thanks.
Last question.
Just a quick suggestion. I noticed that you have not used propylene glycol on your list. Why not? And because we have very good luck with that, with this technology. So several percent of propylene glycol, and propylene glycol is actually approved for clinical, for IV use. Have you tried that?
Yeah, we tried that. It's not working for our model compounds.
Okay, because we were lucky with that and no problems at all. And you don't have to worry about residual.
Okay, thank you very much. We move to the next speakers. Thank you very much.